Good afternoon. We're in the Land O'Lakes boiler control room at their Melrose, Minnesota plant. We are looking at the monitor for the boiler plant control system upgrade, which is still in process. So what we're going to do is cover the balance of plant control systems and the boiler 1 and 2 burner and combustion control instrumentation systems. We are on the screen, the navigation screen, which is accessible from the button in lower left center. The balance of plant systems include the plant steam header pressure control, the condensate level control, the DA pressure and level control, feed water pressure control, including feed water recirc. Then eventually we will have the heat recovery system, the air compressor system, as part of the balance of plant control loops. Down below the balance of plant screen buttons, we have the boilers 1 and 2 burner and control navigation buttons. But let's start with the balance of plant. We'll go to the plant master controller. We click on that, it brings up our plant master screen, which includes faceplates for the plant master pressure controller, the boiler 1 and boiler 2 firing rate or submaster controllers. The plant master pressure controller is responsible for maintaining steam header pressure from whichever boilers are in operation. In this case, boilers 1 and 2. At some point, boiler 3, which is at the other end of the building, may be tied into this, but that is not the case right now. So the plant master pressure control maintains steam header pressure. It does it by measuring the steam header pressure. The actual steam header pressure is displayed in the lower right-hand corner of the faceplate. It's called the PV or process variable. Right now it's 140 psig. This value is also displayed on our plant overview screen as the header steam pressure. The plant overview screen compiles pertinent data from all of the boiler plant control systems. Back on the plant master screen, we see that the actual header pressure is 140 psig. That is also scaled on a vertical bar graph labeled PV, and the range is 0 to 200 psig. When the master controller is in automatic, it will compare the actual header pressure with a set point pressure or desired steam header pressure. This set point is entered by the operator. The operator will click in this field, and on this screen he can type in whatever pressure he wants the steam header to operate at. Whatever he types in will be displayed in the lower left-hand corner as the desired or set point pressure. That value is also displayed on a vertical bar graph with the same range as the pressure transmitter, 0 to 200 psig. So when the plant master controller is in automatic, it compares the actual pressure to the set point, and it will increase or decrease its output to whichever boilers are firing in automatic at that time. The output right now is at 45%, and that is represented on the blue vertical bar graph. It's the output percentage. The operator has the ability to select manual or auto firing rate mode or pressure control mode. In manual, the boiler firing rate will only be what the operator enters in this field. And just like the set point, the operator can type in a firing rate demand, and that output goes to the individual boiler submasters as their set point. You see, I just typed in 45 here in manual, bar graph's at 45, but now the demand for the boiler 1 and boiler 2 submasters is at 45. These are position controllers. This is a PID, or proportional integral derivative controller, which is required to maintain pressure. The submasters merely take the boiler master output, whether in manual or automatic, and I got to get this back into auto because in manual my pressure crept up a little bit. So I'm going to drop this back into auto, and I did that because I did not have a very large difference between the set point and the actual pressure. If I would have entered a pressure set point of like 100 pounds, dropped it into auto, the plant master output would have dropped like a rock because of the controller action. And then the demand, firing rate demand to boilers 1 and 2 would have followed the plant master output, also dropped. And as operators, you know that can create problems with level control. It's generally not good practice. So you're usually best to have the difference between the set point and the actual pressure within 5 pounds before you switch from manual to auto. From auto to manual is always bumpless. Bumpless means that there's no shift in the output when I go from auto to manual rather. But again, based on the deviation, going from manual to auto can sometimes increase the rate of master output change a little faster than one would prefer. There are header pressure alarm set point entries on this screen also. And again, the operator can enter these just like we did with the set point and the manual output. So there's a low and a high pressure alarm. These are analog alarms, meaning they come off of the pressure transmitter. And so, for instance, I will raise the low pressure alarm from 120 to 150, which is above the current header pressure. When I hit enter, we have an audible alarm that went out at the BOP control panel, and the alarm field is backlit red. I push acknowledge to silence the alarm. If I go to the alarm screen, I should see steam header pressure low alarm. I got the low alarm because I told the alarm level to go into alarm if the pressure was below 150 psi. And of course the header is currently at 144. I'm going to change that back to 120. The alarm will clear, and the alarm is acknowledged on the alarm screen. If I click acknowledge, that should disappear. Thank you. So for purposes of demonstration, the high pressure alarm functions the same way. This is an operator entered value, and these are desirable because you want to become aware if the plant somehow has gotten, if the steam pressure control has gotten has lost control, or something has changed which has caused a low steam header pressure or a high steam header pressure condition. That alarm should make the operator aware that he needs to look at something before you lose production due to low steam pressure, or if the pressure goes high, the boiler steam drum pressures will go high, and you may hit the high pressure cutout on the boiler, which would trip the boiler. So these should be set to some pre-warning level where the operator wants to know that he's not close to where he wants to be. There are other alarm entry fields like this on some of the other screens, but functionally they're all the same. In alarm, they'll sound the horn, generate a message on the alarm screen, and backlight red. So going back to the steam header pressure control, the plant master output in automatic will control the firing rate demand of any boilers that are in automatic. If the boilers are in manual, it doesn't matter what the plant master does, nothing will change. One boiler could be base loaded in manual and just allow one boiler to swing. If the boiler submasters are in manual, the manual button blinks to draw the operator's attention to the fact that that particular boiler is not in automatic. I switch the boiler 1 submaster back into auto, and now its output is following the plant master output, as is boiler 2. Plant master output is the boiler firing rate demand. The submaster demand, which is what the SDMD stands for, permits us to enter a bias into the firing rate. The bias is also operator entered. And so what the bias will do is add or subtract from the plant master output. So I've biased boiler 1 3% ahead of the plant master output. And we're not displaying decimals, and the calculations go out far to the right of the decimal. But theoretically, boiler 1 should be firing 3% higher than the plant master output, which is 41. 41 plus 3 is 44. That's what boiler 1 is firing at now. So the boiler 1 firing rate is 44%. That's shown on the blue bar graph. The firing rate demand is the plant master output plus or minus the bias going to the output. Functionally, the submasters are the same. I can bias one boiler up, one boiler down, and the bias is useful if you want one boiler to lead or you want to balance the load on the boilers. These boilers are not identical, and that's reflected by the steam flow meters, indicators we have below each submaster. Boiler 1, for the same firing rate, will put out a little bit more than boiler 2. And that's due, I've been told that there's some restriction in the gas passes on boiler 2. That reduces the total airflow available to burn the fuel, and so end of discussion is that the boiler 1 output for a given firing rate will be a little bit higher than boiler 2. Like the plant master, a boiler can be manually loaded by switching to manual and typing in desired firing rate in the output field. Well, I did not want to do that. I meant to type in 39 and I typed in 30. So boiler 1 dropped like a rock. I typed it back to 39, which is what I was trying to do. And I need to pay attention here because this system is running pretty well, and all I'm doing is introducing upsets into the plant operation. So my output, manual output's 39%. Submaster demand or the plant master output is 44. Drop into auto and you see that my output jumped. So again, functionally, the two boiler submasters are identical. They each have a plus or minus 10% bias capability. Keep in mind that bias is only effective if you have more than one boiler running in automatic. If boiler 1 was the only boiler operating right now, the plant master demand or output was 44%, and I took the bias down to minus 10. Boiler 1 would fire at 33%, but in so doing, the pressure, the steam header pressure would go down. The plant master output would pick up that 10% that I biased boiler 1 down. So it's going to come back and equalize where it needs to maintain header pressure. Again, the bottom line is that bias is only useful if more than one boiler is firing in automatic. We display boiler 1 and 2 steam flow from the respective steam flow meters. Boiler 3 steam flow meter will be brought into this system soon. It will be displayed down here, although presently we have no control over boiler 3 from this system. And the steam flows 1, 2, and 3 are summed into the plant steam flow. And I believe we have total plant steam flow over on overview as well. So that's the functionality of our Plant Master screen. The faceplates we've used were quite a bit of consideration was given to their layout. And we've adopted this layout because this mimics a lot of single loop controllers which were predominant in the control field through the 80s, 90s, and early 2000s. A lot of operators will be familiar with the 3 bar graph displays. Manual auto functionality is either single button or dual button, but the ability then to write a set point or a manual output, again, mimics the functionality of a lot of older analog type controllers. From the Plant Master, we'll just stop again briefly on the plant overview. And this is all view only. There's no operator input to anything on this screen. This is just all information displayed. Not everything is hooked up yet. For instance, the air dryer is functioning, but the dryer status is not connected yet. And again, this will just indicate whether the dryer is on or off. But we have our inlet flow, inlet pressure, outlet flow, outlet pressure, and outlet temperature. These values will also be shown on the air compressor screen. Over on this screen, though, we don't have a run signal, and on this screen we've elected to flash the dryer status button. Again, to draw attention to the fact that if we don't have a dryer run signal and the operator knows it should be running, this should draw his attention that something may have to be reset. Again, the plant overview, all display only. We show our mouse. Where did our mouse go?
You gotta kind of move it around a little bit on it.
Okay. We have status indications on our condensate transfer pumps and our feed water pumps. Again, there's nothing the operator can do on this screen other than view status and plant variables. Going back to the balance of plant navigation screen, we'll pull up the condensate level display. And again, we have kind of mimicked what was on the old condensate level control panel, including these pilot lights, which are status only, and they mimic the functions of the pilot lights on the old panel. So the condensate level system, like the Plant Master, the operator will enter where he wants the level. This is in percent, whereas the Plant Master and some of the other control loops will be in engineering units. For instance, the Plant Master was PSIG. This is purely percent. The tank is approximately 9 feet tall, and the level transmitter has been scaled to display the level as a percentage from 0 to 100. So the operator enters his desired tank level as a percentage. The PV, process variable, is the actual tank level. It's at 53.2%. The operator entered set point is displayed in the lower left. The tank level, these two values should be identical, is displayed to the right of the tank, and the tank level fill is also animated. As the tank goes up and down with the level transmitter, this will fill with the dark blue or decrease down to whatever the actual tank level is. This control valve is what maintains the makeup water to the condensate level. So this level controller, its output is going to this valve. This field displays the valve open percentage. Only up here we have a decimal point on it. In the controller output we do not. There are level switches. These are float switches on the side of the tank. Now we have analog level alarms here, just like our steam pressure alarms. The operator can enter these so he gets a warning if his level is too far away from where he wants it to be operating on the controller. Be the same thing if I put the low level at 60. The alarm field backlights red and flashes. The alarm horn has gone off. And on our alarm screen we have condensate tank analog level low alarm. We distinguish between analog and discrete. The discrete, if either of these float switches is activated, if we hit high level or we go down to low level or low level, you'll also get alarms, but the verbiage on the alarm screen will be different. It will distinguish, it will say digital high level, digital low level, or digital low level. So we'll move this back to 40. In here, in the control room, our entries have to be through the keypad. All of these screens are mimicked out on the control panels out on the boiler room floor. We have one panel for boiler 1, one panel for the balance of plant, and one panel for boiler 2. Each of these panels has an HMI, human machine interface on it, or touch screen. The screens available out there are identical to these screens. Difference is alarm entries out on those screens. If you touch the alarm field, a small keypad will come up and the operator can enter his alarm values on the keypad, click the download button, and it will write it into the program. On this, in the control room, any operator entries have to be through the keypad. We also show various system parameters, values up above the condensate transfer pumps. We have flow in GPM. There's only one flow meter, but we've calculated to convert the GPM into pounds per hour, which is sometimes convenient if you're comparing plant load operations. Condensate temp up to the DA tank. The condensate tank temperature coming back from Proliant and the condensate flow coming back from Proliant. The condensate transfer pumps, the icons are animated. When they're green, they're running. When they're red, they're off. The condensate pump control is done from this field here, but only because on the condensate pump starters, there is a handoff auto switch. Those switches are in auto, which enables us to start and stop the condensate transfer pumps from these 4 buttons. If for some reason you have to run the condensate pump and it's not working from this system, you go out to the starter, which is mounted on the wall opposite the ammonia room. You turn the starter selector switch from auto to hand, and the pump will run. At that time, you'll also, the pump icon will change to the appropriate color to indicate it's running, but we will not get a started indication here. So we can start and stop the respective condensate pumps from these buttons. We also have runtime totalizers in the program, which will display the total hours on each pump. We have a shortcut button from the condensate to the DA tank, but we can navigate either way. From DA we can go back to condensate, from condensate we can go to DA. It's a shortcut. So here's our DA control screen. The DA requires a level controller to maintain feed water in the DA storage tank, and it also requires a pressure controller to deaerate the water in the deaerator tray section. So the level controller controls the makeup water valve to maintain the DA level at whatever value the operator wants it at. And here our set point is 0.5 or 1/2 inch. Again, this is operator entered. The operator decides where he wants to run that DA level when the level control is in automatic. The PV process variable is the actual tank level, and the tank level is scaled from -24 to +24 inches. You can see that next to the vertical bar graphs, how we've scaled it. And we do that so that typically 0, or the middle of the tank, will be the 0 operating level. But this is scaled in inches, as the transmitter is scaled in, calibrated in inches of water. -2 feet to +2 feet. Operator enters the desired level in inches of water. The operator entered set point is displayed down here. The controller compares the actual level to the set point, and in automatic it will vary the output to open or close the makeup water valve to maintain DA level. Set point bar graph, PV bar graph, output bar graph, 34%, and our valve position is 35. And again, that's a difference in display resolution. Level controller is strictly to maintain the DA tank level. On the DA tank at the bottom, we have a temperature indicator showing -15 degrees Fahrenheit. There is a temperature sensor for the DA storage tank that is not connected yet. On this screen, we also show some of the things, duplicate some of the things that were on the condensate display screen. We have the total plant feed water flow, and this will be the sum of all 3 boiler feed water flow meters. Currently, only boiler 1 and 2 feed water flow meters are tied into the system, but eventually boiler 3 feed water will also be summed into here. We also display the feed water header pressure. In the tray section of the DA, we show the DA pressure. The pressure is controlled by the steam pressure control valve. That is the right-hand controller, the aerator pressure control. Operator entered pressure set point in PSIG. The range is 0 to 20 PSIG. PV and set point are both scaled the same. Set point of 10 puts us in the middle of the set point bar graph, displayed down here. The PV now is right on the set point. It's also at 10 inches. PV bar graph is right in the middle. And to maintain that pressure, the steam control valve output is 36%, which is shown up here. Many of these control valves, if they go to 0% output, we will turn the body of the valve red, and that's just to grab the operator's attention in case he looks past the display. Some of them will also flash, but not all of them. Again, it's an attention-getting mechanism just to catch the operator's eye. If this steam valve was closed, the operator might see it and wonder why, look at his pressure and wonder what's going on. Somebody shut off a valve, or is something else wrong? We have alarm set points on this screen as well. We have a high level and a low level set point, a high pressure and a low pressure set point. Again, these are operator entered. I will take the DA high pressure alarm and I'll move it below the actual DA pressure of 10 pounds. And I don't get the horn. So that's something I was working on before I came in here. We will have a DA tank pressure high alarm, but we're supposed to get an audible alarm with it. That's
Go.
Okay, back to the DA control screen. One of my alarm horn functions was not functional. Let's go to the low DA pressure. I'm going to enter 12 pounds. So I've told the system if the DA pressure gets below 12 pounds, go into alarm. The DA pressure is at 10 pounds. I'm in alarm, backlight is flashing. Notice too, when we have an alarm, we have a BOP in alarm flashing, and I hit the acknowledge button, we'll silence it. We're still in alarm, so the BOP now changes to alarm acknowledged. On my alarm screen I have DA tank pressure low alarm. Go back to the DA, I'm going to set the low alarm, and that's still flashing because it's still in the alarm state. I'm going to set the low alarm back to 5 psi. That should extinguish and the alarm will be...
No, stay there for a second. I just want to zoom in so they can see what the alarms look like.
So these are some of the alarms we recently triggered. These have been acknowledged, as indicated underneath the bell icon, which is a little difficult to see. And an acknowledged alarm will turn green.
All right, okay,
Get
back.
a good enough
Yep.
view of that?
Yep,
So I'm
now
going
we're back to full
to
screen.
acknowledge all, and then they should go away because none of them are in alarm. Go back to the DA control screen. So, again, the operator can enter high and low alarm level alarms, high and low pressure alarms. The DA tank also has 3 float switches piped on the external column, just like the condensate receiver tank does. These will change from green to red when the level point float has been triggered. In addition, if the DA level hits the low float switch and there is another low level input, we will shut down the feed water pumps. And when we do that, a message will flash in this box that says feed water pumps disabled, DA low level. And that of course is to keep the pumps from cavitating. It takes more than one low level input to disable the pumps. We don't rely on just a single float switch or the level transmitter signal. So that comprises the DA level and pressure control. Again, as with the other controllers, we can operate in manual. If they're bringing the plant back online, want to inch the pressure, creep the DA tank tray pressure up manually, or feed water into the storage tank at a slower rate than just leaving it in automatic. Feed water pressure. This is a busy screen. We have a pressure controller faceplate. Functionally, it's the same as the plant master, the DA level, DA pressure, condensate level. The operator enters the feed water header pressure that he wants in PSIG. Lower right-hand corner, we display the PV, the process variable, which is the actual feed water header pressure. The controller in automatic compares the set point to the PV displayed on the bar graphs, 0 to 300 PSI scale, and the output will go up or down to ramp whichever feed water pump is running in automatic, increase or decrease the speed to maintain the set point or desired feed water header pressure. This system also includes a feed water pump lead lag control scheme. And that is, the functions of that are in the lower right hand corner. There's a start-stop button for the sequence controller. You see it started. Pump 1 is selected for lead, and so the number 1 feed water pump is in operation automatically from the lead lag, and its speed is being controlled by the feed water pump pressure controller through, we call these 3x3 hand stations. It's basically just a manual auto station. If I wanted to base load, operate this number 1 feed water pump at a set speed, I would drop it into manual, and then I could type in a percentage pump speed output. The lead pump fails, whichever pump is selected for lag, in this case number 3, will automatically start. Pump 2 is in standby right now. We have an indication. The drive will tell the control system that pump 1 as the lead was called to start, and it has started properly. It's start okay. The same sequence for any of the pumps. If the operator needed more feed water pressure, didn't want to rely on the lag, the lead lag control, he could select another pump into lead. That pump would also start. With the additional capacity of a second pump coming on, the feed water header pressure would go up. The pressure controller in automatic would start to back down to slow down the pumps to maintain the feed water header pressure. We have pressure alarm inputs for feed water header low and high pressure, functionally the same as the other. Operator entered. We do have another entry on this screen for the lag pump start. And again, this is a value that the operator enters to tell the system to bring the lag pump on if the feed water header pressure gets down to 185 psi. And actually, I think this might be a little low, but I'm not operating. So right now, as currently configured, if the feed water header dropped below 185, down to 185, the lag pump would start. And it would come up in automatic, try to maintain speed to bring the feed water pressure up to the set point. Each of the pumps also has a recirc line with an automatic recirc valve. That is an open or closed valve. The valve operation is linked to whichever pump is running, and it's also linked to the total plant feed water flow. And calculations have been done and exist in the logic to open the recirc valve if the total feed water flow drops below the point on the pump curve where cavitation below the minimum flow point of the pump. We won't make this a pump engineering discussion. At present, while this valve is indicating open and these two are indicating closed, the valves actually at this moment, 14th of February here, are disabled and they're manually cranked open to maintain recirc. And we probably have a little more recirc than we need, but this has not been fully commissioned yet. We had problems with one of these actuators. That's out for replacement. We also show the feed water pressure, header pressure down here, the discharge side of the pumps. We show the respective boiler feed water valve positions. Again, boiler 1 and 2 feed water valve positions are shown here. Boiler 3 is not tied in yet. And we have the total plant feed water flow. Below the individual pump 3x3 manual auto stations, we have amps, speed, and hours. Pump number 1, we have a problem with the amp feedback from the drive, and that's on the to-do list. We show a percent speed, which does not equal the pressure control output. This has been scaled to the speed range of the drive. At 0% control output, of course the pump doesn't go down to 0 hertz. I believe we're controlling the pump speed from 35 hertz at 0 to 60 hertz at 100%. But that's scaling that's all done in the PLC program. I think that's all we need to discuss in the feed water pressure. Air compressor system is not fully commissioned yet. We stopped development work during the early stages of the project because we knew the air compressors were going to be replaced. So the only valid data on this screen are these 5 yellow fields for the air dryer inlet and outlet, pressure, flow, and temperature on the output. As I mentioned earlier, the dryer run feedback signal is not tied in yet, which is why the dryer off is flashing. This screen needs more work, as does the heat recovery system. We have the graphic overview and all the tags for heat recovery defined, but we have not linked any of the heat recovery system data into this screen yet. Is this a good place to stop?
Yeah. Okay, we'll go ahead and stop here.